Hi students, as previously announced, today's class is online. I'll be down in South Carolina working on the FE exam, so this video has been posted online. For the next homework assignment, homework number 10, that's due on Wednesday of next week, and I've posted the PDF file for that on Blackboard. Basically what you're doing is you're picking a watershed that you're interested in and calculating the curve number for that using the tools that I'm going to illustrate in today's demonstration, and then you're going to be running the rational method, TR55, and national streamflow statistics. So effectively in that homework number 10, what you're doing is you're creating a tutorial for yourself using screenshots and written descriptions so that later on down the road in a few years when you've forgotten how to use this software, you can refresh your memory. So all of the details are explained in the handout that's posted on Blackboard, and that assignment's due on Wednesday. For the remainder of this recording, what it is a demo that I've recorded just now to illustrate how you can use WMS version 11.1 to calculate curve numbers for a watershed. After you've gone through it, do it a couple times so you get the practice. There's a few steps there, so I think repetition is going to be your friend for developing the muscle memory you'll need to be successful in an exam type situation, for example. But if you have any questions, just let me know and I'll be happy to help you out. In this video, I'm going to illustrate how you can use WMS version 11.1 to calculate a watershed curve number. And I'm going to do this in a watershed here in West Virginia in the city of Fairmont. So here's Fairmont, West Virginia. And specifically, the watershed that I'm interested in runs along this Husky Highway. Can you see the stream that flows parallel to the Husky Highway? And I would like to delineate that watershed just before it dumps into Buffalo Creek. So that's going to be my aim, and I'm going to keep this just in case I need to do some comparisons later on. So I'm starting with just a blank WMS project file, nothing yet defined. I go in here to the project, the hydrologic modeling wizard, and I've picked the location I want to save this, and I'm going to call it Fairmont. And save that. And as usual, I'll have to first begin by defining the project projection. I've just installed the latest version of WMS here on my computer, and that's why it isn't set already. If you didn't already have that, you may have previously run it and it may remember the most recent one. But let me switch into NAD 83 for UTM, and all of West Virginia is in zone 17. All right. And I'll switch the vertical, the vertical datum to NAVD 88 and meters for the units. And now here in the selection tool, I'm going to type in Fairmont. Jump the location. All right. So here's that long stretch of straight highway, and what I'm interested in is this creek before it dumps into Buffalo Creek. So this is Fairmont Run here, and this is Buffalo Creek. So I want to make sure that I've got the entirety of the Fairmont Run watershed. So you can see here is a ridge line, and here, but it looks like it extends a little bit further. I think I've got it all in this window because here's the outlet, and if I just kind of visualize the high points here, I think that we've got it. All right, so I've defined the boundaries of the watershed, and now we can see the coordinates are filled in. I'm going to use web services to get my elevation data, but I need more than just the elevation data. So in the past, all we would have turned on here was worldwide elevation data. I'm turning that on, but I'm also going to be turning on two other files as well. I'm going to turn on NLCD 2011. That's the National Land Cover Database, and that gives me land uses. So it's going to differentiate between urban areas and vegetated areas, and it just basically tells you what is going on at the surface. So that's one of the aspects of the curve number. And then the other thing that I need to download is the Surgo soil type shapefile. So let me turn that on. And I'll click download data from web. This is going to take a little bit longer than it has when it's just been the elevation data, because it's going to have to download all three data sets. Now over off screen, since I'm using two screens right now, it prompted me for what resolution I want to use. I'll go with the default. This is suggesting the resolution for the elevation data, just based on how far zoomed in versus zoomed out I am. So I'll click with the default, and you can see at the bottom it was just reporting that it was downloading the elevation data. Now this is asking a similar question, but for the land use data. So the default cell size is 20 meters, and if you were working with a really gigantic area, it could resample that, but I'll just go with the default, and that'll be fine. And it's downloading now the land cover data, and that's off screen here. We get the report that it's getting the Surgo soil type shapefile. Okay. Now over on the left-hand side of the screen, excuse me, you can see that now we have the elevation data like we generally do, but then here's the National Land Cover Database and our soil data. So let me show you what's on the screen. Look at all these squiggly lines. If I turn off the soil shape files, then it gets a lot easier to see our area. It downloads a county at a time, so it gets the entirety of the county regardless of what your specific area is. So these green colors that you can see here, let me switch off the elevation data. So here's the land cover. So red, if we kind of think back to what we were looking at with Fairmont, this is urban areas, blue is water, green is vegetated with no urbanization, and then if you remember, this was kind of the roadway corridor. So with each one of these colors is an assigned land use, and the computer is able to translate that color into a land use using a table of values that we're going to import. So that's the National Land Cover Database that we're looking at, and it was being displayed as an image file that we don't necessarily have to look at if it's getting in the way, so we can turn that off, and it's still loaded into the data for calculation purposes. Let's take a look at our elevation data, and since it's going to require us finding the location that it outlets the Fairmont Run into Buffalo Creek, I'll probably also turn on a map after I've run Topaz. So let me open up the wizard again and get down here to compute flow directions. I'm not exactly sure what the area of this watershed's going to be. I'll leave the threshold for the minimum flow accumulation at 1 square mile till we see what things look like. But I'll compute Topaz. It's finished that. Okay. And with so little of that stream shown, that suggests that maybe I ought to decrease the area required before it assumes there's a flow accumulation cell there. So let me switch it to 0.25, and now we see it going further into the network, into the watershed, 0.1, and now it's beginning to become dendritic. So we'll be able to identify the outlet location with that. But to do so, we will have to turn on a map. So let me get online maps, and this World Street map would be a good one. And it's going to be over in this region, because remember, here's that very distinctive bend. Makes it easy to spot. So when I'm picking the outlet location, I'm going to go a couple of cells upstream of the joined location, because I don't want to have, if I click here, for instance, then it's going to delineate both the watershed I want, but also the upstream area for Buffalo Creek. So I'll go a couple of pixels upstream from that just to make sure I don't get any unwanted area in my watershed. So I'm going to choose outlet locations. All right, create outlet. It's going to go, let's make it here, and then delineate watershed. It's calculating. All right, good. And it looks like I did get lucky in terms of, having the correct project area. And you can see there's that ridge line. So 1.90 square miles. Now the question is, what's the curve number in this? What we're going to be able to do is use this soil data and use the land cover database data, which tells us, for instance, where the houses are. Let me turn off the street map, since over here that's on top of it. I might be able to drop it down behind it. Well, I'll just switch it off. And there's the land cover. So if we go back to the street map, you can see that these yellower shades kind of coincide when there's a little bit of urbanization. The green would be the areas that are undeveloped. Red is maybe commercial and more highly developed zones. So that's going to be really useful. All right. So let's take a look at the watershed without that land cover in the foreground. So we want to find out the curve number in this area. So I'll go back into the hydrologic modeling wizard. Let's skip forward a bit. All right. Ultimately, we're going to use this in either TR55 or HEC1. That's the two main watershed models where you'd utilize curve numbers. And so let's just go with TR55, which we've used before, and click initialize, and it kind of copies over anything it knows already into TR55, such as the watershed areas. And now with the TR55 model initialized, what we're going to do is close the wizard and talk about some of the elements that are here in the Project Explorer. You'll notice right now that we've just got a single coverage. There's just a drainage coverage. And if we turn that off, you can see that our watershed boundaries are no longer shown on top of the map. So the drainage coverage is there by default. It was created when we delineated the watershed. But what we want to do is take this soil type shape file and create a soil type coverage so that we can use that for calculations. So right click on the word coverage, and we're going to create a new coverage. And the type of cover that we're going to create here is a soil type. And it's going to be called soil type here, and just click OK. And so there's this new empty soil type coverage that's there. Now down here in the GIS data, we're going to right click on this GIS coverage, the GIS data that we want to put into the soil type coverage. And the first thing we want to do is join NRCS data. And we're joining the shapes to some data that was also downloaded. And maybe I can take a moment just to show you of the thing that we downloaded with that soil data. It was in this folder, Fairmont Surgo. You'll notice it's a pretty big folder. It's 65 megabytes of data. A lot of it is not just the shape file, but different parameters that comes from the web soil survey. If you remember, we manually kind of went through and looked at, there's so much data, like different crop suitabilities and moisture content under different temperatures, tons of information. And so what we want to do is we want to join some of these data files to the shape file. The shape file just shows kind of the curves and the locations of polygons, but we want to join the soil texture and the hydrologic soil group. And occasionally there might be some field that's empty, like there may be one of the polygons that it doesn't have data for. So if we click fill blank values, it gives you the option of, if there is any of the polygons that it doesn't have data for, what should it assume? And so D would mean you're just assuming the worst case scenario, fill it with that plastic soil type. And I guess if we're trying to be conservative, then filling in the empty data with soil type D is fine. For now, I'm not going to have it fill the blank values, just because I kind of want to see whether we have any blank values. And if we filled them in, then it would be tricky to differentiate between those polygons we have data for and those that were filled automatically. So for now, I'll say no, don't fill the blank values, but we are joining the data. So click OK. And so we've joined the database with the polygons. And so what we know now is that these different polygons, if you use this identify tool, then it brings up some information about each one of these. So it has hydrologic soil group B. So that polygon I just clicked on, here's, it looks like a really small polygon of hydrologic soil group B. Here's one that is also B. Lots of B soil. They must have better conditions. Here's a C in Fairmont than they do around here. All right, so we have joined that data so that those polygons now have A, B, C, or D classifications according to the hydrologic soil group. Next, I'm going to right-click, and I'm going to just to reiterate, what we did was we joined the join NRCS data. So we did that already, and now I want to highlight all of the polygons that are in my watershed. And so let me select them, and I'm just going to click a box like this and put the entirety of my watershed in there. And it's selected some, but maybe not all. If I zoom out to the full extent of the map, let's see, you'll notice that some of the polygons, like rivers, extended well beyond our project area. But I just wanted to make sure that I had all of the polygons that are inside of my watershed are selected, and they are right now. So they're selected, and now I'm going to do shapes to feature objects. And so I'm taking this GIS data and putting it into the soil type. So shapes to feature objects. And I'm going to take these shape files, the GIS data, and it's going to go into the soil type coverage. Okay, so next. And we want to scroll over a bit. Oh, it looks like there are some empty polygons potentially. Maybe I better go back and just fill those in and make sure that, now that I know there were some empty ones. Okay, so let me go back to this previous step. Right click, join NRCS data, fill blank values, and we'll fill it with D just to be on the safe side. Okay, and now if I go back to shapes to feature objects, we're joining the GIS data to the soil type coverage. Next, now if we scroll over, now there aren't any empty hydrologic soil group classifications. Everything is going to be mapped. These different symbols have been mapped to hydrologic soil groups. And these are different classifications. If you remember to the web soil survey, when we were clicking on the different types, then it would give you like the full name of the soil type, where it's typically found, what its characteristic hydrologic soil group is, and so on. So we're just joining this together, click finish, and now if we turn off this one, and we can turn off the street map, you'll notice that we have, let me turn off the drainage coverage as well. So here are these soil type polygons that are in a coverage. So in the drainage, we've got the watershed boundaries. In the National Land Cover database, we've got the land use. And if we want to look at it, we can turn it on here. So this is the land use. Here's our soil type. Here's the elevation contours. So here in the drainage, in the hydrologic modeling module, we can go into the calculator and compute GIS attributes. And we're going to use coverages. For the soil type, we're going to use the soil type coverage. We're going to use the grid. This is a grid, the land cover database for determining land use. And then we have to import a table that explains the relationship between what combination of land use, soil type gives us what curve number. And here is the file that it's going to use to translate that. There are different numbers that go along with those colors. Here's the name of what that number corresponds to, whether it's a developed area or a forest area or wetlands. And then what is the curve number that's associated with a type A soil, type B soil, C, and D. Okay, so I'm going to have to tell it that this is my table for translating land use soil type into curve numbers. So here, import. Here's the land use soil type table. And when I click OK, it's going to calculate the composite curve numbers, and it'll give me a report when it's finished with that kind of explains how much of different soil types and land uses there are and what's the overall weighted curve number for this entire watershed. So it's going through and calculating that, and it's asking me how should we open up this curve number report. So let me open it with the notepad, and then here's what we know about this watershed. So the weighted curve number is 60 for this watershed. We've got quite a bit more type B soil than we would, in the Huntington area. And remember those areas that were classified as soil type D when really we weren't exactly sure what soil type it should apply to? What you'd want to check is to see how much of the area is to those assumed soil types. And so it's a much smaller fraction of the area compared to most of the area is either deciduous forest on type C soil. We've got some grasslands. You'll notice there's a fair amount of developed open space. But these ones that were assumed D values are so small on the area that hopefully it won't have too much of a negative influence that we had to use that assumed soil type. So that curve number of 60 has now been, if we go over to TR55 and open up that window, the curve number of 60 you can see has been copied in to the TR55. And so we could calculate the time of concentration. And if we use the lag time SCS method, it's got the watershed length, which it calculated from GIS attributes, the curve number, which we just calculated, the watershed slope, which it knows from looking at the elevation data. And so we can calculate the lag time from that. And with the lag time defined, it also defines the time of concentration. And we have a type 2 rainfall distribution in West Virginia. So if I was interested to know, for example, what kind of runoff I'm going to see for, here's the runoff depth for a certain amount of rainfall. If we had 2 inches of rainfall, then here's my runoff. And because I know the area of the watershed, I can even have it compute the hydrograph. And with that computed, I could look. Let me close that so I can bring open the hydrograph. I had opened it in the other window. I'll drag it over here. So here is what my hydrograph would look like. So there you have it. That's how you calculate the curve number in an automatic way. This is maybe the most in-depth in terms of having to do some manual steps, and there may very well be a way within the wizard to do that in a straightforward way that doesn't require you to create your own coverages manually. That's kind of just how I know how to do it, creating the coverages manually. You can experiment around and try for yourself, but just to summarize, if I'm going to start from scratch here, the main process is to delineate the watershed after we have, let me create a new file name here, Fairmont try 2. Okay, so we've got the area defined. I'm surprised it doesn't know it from last time. Oh, it is. Yeah, that is. For a moment, I thought that said Barbersville, but it's Barackville. So this is our bounds. So there's the coordinates for it. We can download. The 3 things we need is the elevation data, the 2011 National Land Cover Database, and the Surgo soil data. Click download. It'll prompt you for the resolution of the DEM, prompt you for the resolution of the land cover file, and then it'll begin downloading the soil type data as well. That's doing that over here on the other screen. So it's getting that. It's the largest of the three. It creates them and compute topaz. It finishes that. Let me turn off these things to make it easier to see. And what we want is see the curve of the larger Buffalo Creek. I'm going to drop my outlet for delineation just upstream of that location and then have it delineate. Okay, and it's delineating the watershed automatically. It's got the area, but it doesn't yet have the curve number, and I want the curve number. So what I'll do is I'll create a new coverage, right click, new coverage, and it is a soil type coverage. Okay, so the coverage is created. I'll go here into the shape file, join NRCS data, and fill blank values with soil group D. Okay, and I'll go up here into I need to turn on and select which shape files. You could select them all, but I'll just select the ones that I'm going to need to put into that new coverage. So I've selected them. Now, mapping shapes to feature objects. We're going to map this GIS shape file into our soil type coverage. Make sure that it knows the hydrologic soil group is this, what we see from the data file is hyd group. That's going to be mapped into the SES soil type characteristics. That's what we're going to need for calculating the curve number. Finish. All right, so now we can switch off this one, and here are our soil type polygons. And depending on which of the coverages you have highlighted, one goes into the background, one is in the foreground. It doesn't matter which one is selected when we go into the calculator. In the hydrologic modeling module calculator, we're going to compute GIS attributes. We want to calculate the curve number using the soil type coverage and the land use grid. We have to import this translation table. You can see that it knows which color numbers go along with what land use types, and then which letters of the hydrologic soil group corresponds to what curve number for the respective land use. Click OK. Goes through the process of analyzing and calculating a weighted curve number. Then in just a moment it's going to prompt us to see which program we should use to open up the report. It's just a text file, and you can save that text file someplace else once you open it. So if I wanted to save a copy of it in my project folder, then I could do that. Curve number report. It's saved. All right, so we've got all these curve numbers, the weighted curve number 60.2, and if you open up the watershed, it thinks it's in the HEC1 model now. Let's go into TR55, open that, and see it has copied the new curve number of 60.2 that it just calculated into every place that it would need to know the curve number. All right, so that's just an illustration of how to calculate the curve number for a watershed. And what I suggest you do is go through this same process both for the Fairmont watershed, but then also for the watershed that you used for homework 1. The watershed you're interested in, try and calculate the curve number for that watershed as well.